So I finished class a bit early last time, unbeknownst to me, so I decided I'm gonna make this recording with some of the problems on go back in and selective repeat solved here for you, with you, just so you have a few more examples than what we did in class together. So I'm gonna start here on your textbook. Problem number 22 is the first one that has go backhand as the topic. So the problem reads, consider the go backhand protocol with a sender window size of 4, sequence number range of 1024. Suppose that at time t, the next in-order packet that the receiver is expecting has a sequence number of k. So my receiver right here is expecting to receive k. So if I draw something similar to what we did in class, that would mean, say here is my packet k, so this is my next sequence number, right? Which would then mean that I received, k minus 1, k minus 2, k minus 3, and acknowledge that, right? This is the receiver. So all of these, let me try to kind of color them, would have been received and acknowledged, right? So the question goes on to say, assume that the medium does not reorder messages, which means that when packets are in flight, they don't get reordered. Answer the following questions. A, what are the possible sets of sequence numbers inside the sender's window at the same time t, okay? And justify your answer. So, okay, let's think about what's happening at the sender, right? So at this time t, at the receiver, I'm expecting to receive k, right? So the question is, what's happening at the sender? So I just mentioned that if I'm expecting to receive k, I have definitely received k minus 1, k minus 2, k minus 3, and acknowledge them. Remember, acknowledgement here is cumulative, right? We're talking about go back n. So, these packets could have been in flight, say they act for k minus 1, k minus 2, k minus 3, and so on and so forth, right? Could have been in flight, right? Or they could have been have been received at the sender, right? So let's suppose that the sender did receive all these acknowledgements, right? So if the sender did receive all these acknowledgements, what would be the window then at the sender? Would start with k, right? So this would be my send base, because everything else has been acknowledged before. So my window would be from k to k plus n, which in our problem is 4, but I'll just keep it as n minus 1, right? So these would be the ranges of my window, right? So if I draw again like the way we did in class, right? So everything before k, so here's my k, everything before this has been, received and acknowledged. This is my send base right here, and then anything that I can fit after that, right? So it would be 4 because my window here for the problem is 4. So this would be, the possible values for my the window at the center. So that's the scenario where all these acknowledgements were received. What about when they are not? So let's suppose that acts were not received, right? So if the acts were not received, then now what would have happened is that I could be, my window then could be k minus n right here, right, up to k minus 1, right? So just before what I'm expecting now, which is packet k, right? So if all those acts before k were lost, then that would mean that my sender window would then be sitting in this interval right here, right? So if you look at this, it's either this situation right here or this. So you could say then that the sender window would begin somewhere in the range of k minus n and k. So I'm just getting the beginning of the window here and here, right? So my sender window will be sitting somewhere here, depending on how many acts made it back to the sender, right? And if all of them made, then it would start at k. And that would be the answer to this problem. Okay, next problem 23. it says, consider the go back and selective repeat protocol. Suppose a sequence number space is of size k. What's the largest allowable sender window that will avoid the occurrence of following such as that in figure 3.27 for each of these protocols? We saw this figure in class. It was the slide where I had the problem with selective repeat, which also happens for go back n, by the way. So we had that scenario. If you remember, there was a curtain, and the right side of the curtain was the same at the top or the bottom of the figure, despite what was happening at the left side was quite different, right? So we had the receiver expecting a sequence number 0 packet with sequence number 0, and at the top he was receiving a new sequence number 0, which was what he was expecting, so that was the correct thing. But at the bottom, unbeknownst to the receiver was receiving actually a copy of the older sequence number 0 packet that had been sent before. That packet was retransmitted, and the receiver was erroneously taking that as if it were a new sequence 0 packet, right? So how do we avoid that is what this question is about, right? And I kind of alluded to the answer already in class, so let's look at that. So if you think of how we solved the problem just before this and assume that the lowest sequence number that the receiver is waiting for is some value k, right? Oops, let me try and get something that I can write with here. So here's value k, right? So I'm waiting for k, so this is my next sequence number, right? So the window then at this receiver would be k, and then k plus n minus 1, right? So this would be the range. So the least significant, if you will, edge, and then the leading edge at the other side, right? So, and n, of course, here is my window size, right? Window size. So if this is the receiver, right, what does this imply? This implies that I have received k minus 1, right? And n packets beyond that. I have received and acknowledged them. If I hadn't, my window would not have used, my next sequence number would not be k, right? So this implies that I have received them and I have acknowledged them, right? So I know that I have acknowledged packet k minus 1 and all the n minus 1 packets before that, right? So a window worth of packets, n minus 1 here and then plus 1 here, making n, right? So n window, a window worth of packets, right? Yeah, spelling is wrong here, but you get what I'm saying. So so now I know that these packets, though I have sent them, right, these acknowledgments, I'm not sure whether they were received or not. So I may have, those packets may be in flight, right? They might be, so my k minus n, I may have these acknowledgments here, k minus 1, right, in flight. Right, so heading back to the sender, right? So these are my acts heading back to the sender, right? If these acts have not been received by the sender, then where would the sender window be? So the sender window would then be k minus n up to k minus 1, right? Right here. So this would be the sender window. If none of these acknowledgments right here at the top, made it back, right? So if you look at the lower edge, let me change the color, the lower edge right here, and the upper edge right here for the receiver. So this is the lower edge of the sender window, and here at the top we have the upper edge for the receiver window. So I have to make sure that there is no overlap between these two. So it's as if I wanted a window that would start from k minus n all the way to k plus n minus 1, which boils down to 2 times n in width, right? So my sequence number space must be at least, so k must be greater or equal to 2 times the window width, n, in this problem. So that's the solution, okay? So next is problem 24. Oops, I have still the red in here. So problem 24 is actually a true-false question. It does ask you to justify your answer, which I told you my true-false question in your exam will not ask you to justify. So A says here, with the selective repeat, so let's look at selective repeat protocol, it is possible for the sender to receive an acknowledgement for a packet that falls outside of its current window, right? So you have to answer whether that is true or not. We saw examples of that in class, so let's make up an example here. So say, you know, we're going to use a small window size. So say the sender, so I'm going to draw like we did in class. So this is the sender, here's the receiver. Say the sender sends 3 packets back to back. Okay, so I have a window size of 3, so I send packet 1, 2, and 3. Okay, and then, you know, the receiver then sends the X for each of these packets, right? But let us just say that for some reason, okay, and I'm going to change color, these packets are delayed, so they don't make it back on time. So the timer for these packets here actually expire, okay? And remember, they are individual timers, so I'm going to retransmit them because the timer run out. So say right here, I'm going to try to squeeze them here before, just so my timeline makes sense. So I'm retransmitting 1, 2, and 3, right? So what would happen then is that the receiver will acknowledge, right? I have already received these guys, so it's going to re-acknowledge them. But, you know, while these got retransmitted, right, my window moved forward. Right here, once they acknowledged here, although they were delayed, they made it finally, right? And my window can move forward to 4, 5, 6, right here, right? And then now look at what's happening here. I'm receiving acknowledgement for something for 1, 2, and 3, and these are outside of my window, right? So this means that this sentence is true. This is selective repeat protocol, and it's possible for the sender to receive an acknowledgement that is outside of its current window, right? So it's true. Now let's look at B. So that was A. B says with go back N, it is possible for the sender to receive an ACK for a packet that falls outside of its current window. So it's the same thing, very similar here. It's just that acknowledgement is cumulative in the case of go back N. But we can make up a very similar scenario, and you can show again that yes, this is true, this is possible. So this is also true. C. The alternating bit protocol, we haven't quite discussed this one, so actually C and D I'm going to skip, but alternating bit protocol is the same as selective bit protocol with a sender and receiver window size of 1. So it's called alternating bit because you can have a 0 or 1 only, but I'm going to skip these, so we won't solve C and D because I haven't talked about these two in class, okay? So this is it. This is pretty much, yeah, there are only these 3 questions in the book, but there isn't much else that can be done here. As long as you understand these protocols well and the difference between them, you should be capable of solving any problems. You have a few more examples, but you have the solutions to those already in the study guides that I published online, so make sure you check those too, okay?